All right. Well, good morning, and we'll take a look. So I've posted some information regarding the Kaggle competition. I've actually launched the Kaggle competition, and just want to encourage you all to join and I don't know. I guess explore. um, you will notice homework three. Okay. Um, will kind of part of homework three is to get started with the Kaggle competition. So there is a link right here, a link to join the Kaggle competition, and this will take you over, I think, to our competition page. There's going to be two Kaggle um, projects, okay, two I guess, prediction projects. So this one is the regression project where you are predicting a numeric variable, and then the other will be a classification project. Okay. The so you'll find a link that says to join the Kaggle competition. This is a link reserved for our class. Now, what you will need to do is if you do not already have a Kaggle account, you will need to create a Kaggle account. And this is important. When you create your account, make sure you put in your first and last name that matches what's on the roster, okay, for our class. And that way I can kind of make sure every student is, has joined Kaggle and is participating. Maybe I'll add that too here. Each student should create their own Kaggle account using their first and last name, okay? So, I mean, your username can be whatever, but then in the details of your account, make sure you use your proper first and last name there, okay? And then, and everybody will need to join. And then on Kaggle, there's the ability to create teams. So, you have, I think a lot of people have found teams and groups. I will say, like, sometime tomorrow will be the deadline. And if you are not, if you haven't been assigned to a team, if you haven't found a team or group, I'm going to just kind of arbitrarily assign whoever's left over to a team. Okay, so make sure your information is on there. And if you are, I guess if you haven't filled out any information on this Team Finder page, I will just put your email address so at least your teammates can contact one another. Okay, but anyway, yeah, make sure you find a team, and then if after tomorrow you haven't found a team, I will just arbitrarily assign whoever's left over to different teams. Okay, but anyway, so once you have your teams and whatnot, you will go to Kaggle. You'll create an account, and then someone on your team will create a team, and then you will join that person's team. Okay, it doesn't. So I guess there's going to be a de facto team creator. It doesn't matter who it is. That person's not going to get like any extra points or anything like that. Just somebody has to create the team on Kaggle, and then you'll have the ability or the option to join someone's team on Kaggle, and then you'll submit your submissions and everything like that there. Okay, I will talk a little bit more about the project itself later, maybe later today or maybe later this week. But basically, when you join, one of the tabs here will be the data tab, and you will see kind of a description of the different files and different variable columns, and you will have to make predictions based based on this. Okay, there's a bunch of kind of detail files that you can combine, and then you also have probably the two main files that you'll be looking at will be the train and the test. Train has predictor variables and the output, and then the test variable has everything except I guess order total and log totals removed. So your job is going to predict the variable log total, okay, which is basically the total sales, okay, total amount in sales, where yeah, I think in the order total is going to be the dollar amount, and then the log total is log base 10 of that order amount. So so I'll talk a little bit more, but these are descriptions about some of the data there, okay? And there, again, there's going to be two competitions or two projects. So this first one, the regression one, is going to close, is going to end September 5th, and then the classification one will end just under a week later, probably like the 11th, okay? So basically when our course ends. So that way there's a little bit of space between the two projects there. Okay. All right, let's take a look at today's content, which is going to cover chapters 9 through 13. Okay, or well, we'll see how much we get through. But this is really where you will, I guess, learn some of the techniques where you can create different models and then compare them and try to judge which ones are going to be effective. Okay, because you know, as far as we do data mining and predictions, you know, we're going to be creating different potential models, and some are certainly going to be better at predicting values than others. But how do you measure and how do you evaluate which one is better? How do you kind of tweak the different parameters of the model? How do you affect, you know, do a whole bunch of different, test out a bunch of hyperparameters kind of in an efficient manner? And that's what these chapters will cover. And so I encourage you to continue doing your reading in the textbook. And so we are going to take a look at this material from chapters 9 through 13 today. Okay. So so read through this. The documentation is also going to be helpful. Okay. So Tune is the so again, within Tidy models, there's kind of different sub packages. Each of those contain a set of functions that are useful. And so Tune is the package that allows you to kind of try out different hyperparameters of your model, just testing out different values of your hyperparameters. Yardstick is the way we measure the effectiveness. So you know, our most common measure of model effectiveness will be root mean squared error, but if you want to evaluate using some other kind of metric, those are all kind of included in Yardstick. And then workflow sets allows you to try out a bunch of different workflows and compare them you know, rapidly without kind of doing this very manual process. Okay, so the way we'll do this is we'll start by loading up our packages, and I'm going to kind of follow along right in my own RStudio here. Okay, so I'm going to load up Tidyverse and Tidy Models Okay, and so we'll follow along in this as well. All right, so the first thing we'll do is we'll kind of pick up where we left off. And so this involves kind of creating our initial splits of our data. So we're going to take our total available data and split it into our training and our test set. We are continuing to work with the Ames housing data set, where we are going to use attributes of the house, such as the gross living area, the number of bedrooms, number of bathrooms, the year it was built, all of those different variables to try to predict the sale price of the home. Because sale price is heavily skewed, we will take the log of sale price that reduces some of the skew in the data, and that's what we are going to predict. Okay, just because when you have heavily skewed data and you're using root mean squared error, it's those outliers will have a significant impact. So that's what we were going to do. In our Kaggle competition, I'm also going to ask you to predict the log of the sales total, again, because the sales total numbers are also very heavily skewed. So predicting the log will improve that. Okay, we have a recipe. The recipe is our way of pre-processing our data so that it is in a form that is going to work well with our prediction systems. So a lot of this involves making numeric predictors, taking our categorical columns and making them numeric so we can put them into our model, doing other kinds of transformations. And so just to kind of recap what our recipe involves, we begin with a recipe that tells Tidy Models the variables that we're going to use. So we are predicting sale price. That comes before the tilde. After the tilde comes all of the variables that we will use for our predictions. So we have neighborhood, that's a categorical, a nominal variable. We have gross living area, that's numeric. Year built is numeric. Building type is a categorical or nominal variable. So you have nominal and ordinal variables. So this nominal means there's no inherent order to the categories, and ordinal would be there is an inherent order to the categories. So you have neighborhood and building type. Those are both nominal. You have also latitude and longitude. These are numeric predictors. Basically, it's location, north, south, and east, west in the geography, and it's coming from our training data. We do a few pre-processing steps. So one, we are going to take the gross living area and take the log of that. Okay. We also are going to replace neighborhoods that show up very infrequently in our data set and replace those with other. So there's, I don't know, a couple dozen neighborhoods in our data set. Some of them show up very infrequently, and so those are going to just be grouped together into another category. We set a threshold of 0.01. And then now that we've done that to our categorical variables, or our nominal variables, we will turn them into dummy variables, which basically makes picks one of the columns to be your baseline, and then if it's any value other than that one particular category, it will be a 1 or a 0. And so it does this for, this is going to add a bunch of columns into our data. We get a bunch of 0s and 1s, and that's going to do it for both neighborhood and building type. Okay. We want to include an interaction term. And so we are going to multiply gross living area with the building type dummy variables. So building type, these are going to be a bunch of dummy variables. You'll have a dummy variable for if it's a condo or a duplex or things like that. And we are creating interaction terms there. And then we're also going to do nonlinear transformations to our latitude and longitude variables by making natural splines out of them. Okay, And so this allows for a little bit more flexibility as far as predicting what the effect of latitude and longitude. Otherwise, you'll have, if you don't do a natural spline to latitude and longitude, you'll end up kind of forcing a linear relationship, which would basically say, the farther east you go, the more valuable your home is, and the farther west you go, the less valuable your home is, or something like that. And by doing a natural spline, you can say, as you go east to west, sometimes the values go up and sometimes the values go down. But we're taking into account the that north, south, east, west information there. Okay, so this is just a summary of all of the different steps that appear in our recipe. And again, more details on this in last week's lecture. We establish a workflow, okay? A workflow consists of a recipe and a model. So we have pre-processing steps and we have a model. And this pairs them together, and by establishing a workflow and using a recipe, it handles the important pre-processing steps in a clean way to avoid data leakage. So I don't have, say, a scaling operation here. A scaling operation would involve subtracting off the mean so that the mean is 0, and then dividing by the standard deviation so that the resulting standard deviation is equal to 1. When you do that, the proper method is to calculate the mean and the standard deviation based on your training data only, and you have to kind of keep track of what numbers you used and apply those same numbers to the test data, okay? And if you have, v-fold cross-validation or something like that, you have to do that for each different fold. And so that can get kind of messy, and so therefore, by using a workflow and having a model and a recipe there, it handles all that efficiently for us. So we're going to start with just a simple workflow where we have a linear model and the recipe that we've created. And so this is going to be our LM workflow, linear model workflow, and this is established by starting off with an empty workflow, adding our recipe and our model. Okay, and here I have add model, add recipe. We could swap the order, and it will be fine. And then what we do is we take that workflow that we've established, okay? So the workflow just establishes the steps that you're going to do, and then we fit that workflow to the training data. And what this will do is it will do all of the pre-processing steps in our recipe. It will estimate the coefficients necessary for a linear model. And so the result of that is the LM fit object. This is our fitted workflow. This will contain our parameter estimates and all of that information. And then so now we can start to evaluate, create other models, other workflows, and start doing some comparisons here. Okay, so again, just a summary, we create the model. It's a linear regression. We use R's LM engine. We create the workflow by adding the model and the recipe, and then we fit the workflow to the training data. Okay, so that's where we've left off from last week. And so now we want to start to measure our predictive performance. So we have to evaluate our model, okay? And again, the kind of the state of machine learning these days is we are less concerned about kind of the underlying assumptions and the probability models and all of those things, and we are more concerned about its predictive performance. So, for example, one of the things that you test for and check in, say, your linear regression course is you look at the residuals to see if you notice any kind of patterns of residuals, to see if any of your assumptions are violated, right? One of the assumptions is that the errors are normally distributed with a mean of 0, and you don't want to see any kind of pattern in your residuals. A lot of times you might see kind of non-constant variance, and that would be a violation of your linear model assumptions. But I guess in a lot of kind of modern contexts, we won't worry so much about that. So a lot of times your assumptions might be violated, and you say, well, our assumptions might be violated, but it's still making good predictions. I don't want to say this too much, though, because having a good understanding of the probability models, I think, will make you more effective and will help you. Like, if your models don't have good predictive performance, you might look at some of the underlying kind of probability things, and you might say, well, the reason why it's performing poorly is because these assumptions are, clearly being violated, okay? And so having an understanding about which assumptions are being violated can give you insight as far as how you should improve your model. But you might find that even if certain assumptions are violated, your model has good predictive performance. And that seems to be kind of just the most important part, is if, our ability to make good predictions, okay? So, this chapter in our textbook is all about measuring performance. There's a large part of the chapter 9 is measuring performance for classification models. And right now we are dealing with regression, so we'll talk about the classification stuff later, okay? So classification is, if you're trying to predict categories, how do you evaluate your performance there, right? And, our most simple measure is like accuracy. Did I predict the correct category? But if it's, but there's issues with just using accuracy. But anyway, that's, we'll worry about that later. Right now we are just looking at measuring performance for regression models, okay? So just to kind of get a sense, we're gonna just say, take our fitted workflow, okay? So this is LMFIT, this is the result of fitting our workflow. So this includes all of the pre-processing along with our linear model. And we say, all right, now go ahead and make predictions on the test data set, okay? So just to kind of take a step back, we are not following the best practices at this moment, okay? Because we're taking, this is all our data, and right now all we've done is we've split it into a train and a test, okay? And so right now we are using the training, and then we're measuring performance on the test, okay? This is just in the beginning, just to kind of show you how do we measure performance, okay? In reality, you want to keep this all the way to the very end. And so you are going to kind of do some cross-validation here by doing kind of, this will be like fold 1, and you will have kind of your assessment and validation, right? So you'll kind of split this, and you will. So we'll do this just in a moment. But right now we're just doing the train versus the test. Okay. Okay. So here I'm just taking the fitted workflow. I'm making predictions on the test data. Okay. And on the test data here, I'm saying my new data is basically the test data without the sale price. I think it would still work even if I left the sale price in there, I don't know. But anyway, I'm saying, okay, now make predictions for the column that's missing. We throw that into our prediction set, and these are the results. This is just all of the different predictions. And so the way we are going to measure performance is we compare our predictions versus the actuals. That's going to give us our residuals, right? So here I'm going to take our test results and I'm going to attach another column. And so, with the tidyverse notation, I'm doing kind of operations within some of these functions, right? So aims, test, pipes, select sale price just selects the sale price column. And so I'm saying bind the columns between our predictions and our sale price, and this is what we get. So we have our predicted values along with the actual values of sale price. Okay, so I'm going to go ahead and I will run those steps. That's the recipe. This is our workflow. And then we are going to make our predictions. And here is our predictions compared with our actual values. Okay, so far so good. And again, this is log, so I could let's see, I can do 10 raised to the I don't know what it is. If I want to do mutate, all right, so predict actual, it will be 10 raised to the dot prediction. So this is what the actual predicted value is. I'm sorry, maybe predict actuals, I don't know, predict dollars, and then we'll do actual sale price dollars. Will be 10 raised to the sale underscore price. Okay, so this is, we're doing log predictions, and so this is what we're predicting what the actual value is, versus if we wanted it in dollar amounts, not the log amount. These are the different numbers, okay? But again, we're dealing with the logs so that we don't have to deal with extreme outliers and whatnot. So, but you can just to put this in different context, 116,951 versus 105,203,000 versus 244, 191,000 versus 189, things like that. Okay, so anyway, this is our column of predictions, our sale price, and we can plot how different these things are. So here is just a plot where we are comparing sale price versus our predicted sale price. Okay, and with what we're hoping, okay, perfect prediction everything would fall right along this diagonal line here. And so we see, overall, we're kind of okay. It seems on the higher end, we're not predicting as high, and on the lower end, we're predicting higher than what they actually are, and that's tends to be the case because regression towards the mean. But this is our fit there. Okay, so I just said, hey, on the x-axis, put the actual sale price. Versus what you on the y-axis what you predict. Okay, and we can measure things like RMSE. Okay, and so you can take this function RMSE, root mean squared error. Okay, and that's going to you're just going to give it this column this data frame. And you give it the two columns of your predictions and your actuals, okay? So you'll say the truth is going to be the sale price, the estimate is going to be your dot prediction, and it's going to measure the root mean squared error, and here our root mean squared error is 0.0736, Sometimes you want to compare multiple metrics, okay? So you might want to compare things like root mean squared error and your R-squared value, and this is the mean absolute error, okay? And you can get all of these values here, okay? So, and just to kind of illustrate that these are legit, okay, whoops, I can calculate all of these things myself. So I can take so we'll do like residual will be the dot actual, so sale price minus our prediction. So these are our residuals, okay? And then I can then mutate the squared residuals. Square residuals is going to be my residuals squared, okay? So this is be my squared error, and then I can take, I can then summarize, and we'll do, what do we want? We want the mean squared residuals, so this will be MSE, is going to be mean of square residual, okay? And then I can take the square root of that. So what I'll do is I will pull that, and then I'm going to square root it. Okay, and so you can see the square root. This is the square root of the mean squared error, and the mean squared error is just I've taken the difference between sale price and the prediction, I squared them, I took the mean of all of them, and this is what we have. Okay, but you can just call RMSE on your Ames test residuals. Truth is equal to sale price. Estimate is your dot prediction. Okay, and then I'm going to select the dot estimate, and I want to just pull that value. Okay, and you can see it's the exact same. It's the exact same number. Okay, so you could manually do this yourself. Calculate the residuals, square the residuals, take the mean, take the square root. Okay, or you could just call RMSE, right? And so again, there's nothing in the tidy model set that you can't do manually. It's just this makes it way easier, right? It's just one line there. Okay. Same kind of things with the R squared. Mean absolute error is what the MAE is, and so you can create things like metric set, and then you can say, hey, I want the calculate the metric set. Okay, so the way this works is you call metric set, and we're going to call this Ames metrics, and this basically effectively creates a function called Ames metrics. Okay, where you put in it's kind of like RMSE is a function that calculates the RMSE. Ames metrics is now a function that will calculate the metrics that you just defined or selected in your metric set. Okay, model metrics by itself, not very useful, okay? Metrics are really only useful when you're trying to make comparisons between multiple models, right? Like if I tell you, oh, they took this exam and they scored 7.9 points, and that's not useful by itself. Okay, you say, okay, 7.9, is that good? And it's only useful when you can compare it to others. Okay, and you can say, okay, oh yeah, 7.9 is above average, or 7.9 is below. So chapters 10 and 11 are basically going to focus on allowing us to kind of compare our model performance between different models, okay? And so what we're going to do is we're going to use cross-validation, okay? And we introduced a little bit of cross-validation here. Chapter 10 shows some of this here, and this is what we're going to basically be doing. Okay, so we have our different resamples, our different folds here, and we're going to look at the analysis set to make our predictions, and then we measure our performance against the assessment set. Okay, so here I'm going to just create a new model, and this is going to be a random forest model. Okay, now I have not talked about how random forests work in this class. Not yet. I guess that will be a future lecture, just so you have a little bit of context as far as what it's doing. But basically, a random forest is a way for us to make predictions. Okay, it's different from a linear model. A random forest consists of a decision tree, and a bunch of decision trees kind of averaged together. So a decision tree basically says, hey, if you had to split your data into two, how would you split it? And you might say, okay, well, let's split it based on gender, all right? And we'll put, we'll split it, and we'll say, for this side, this is what we would predict, and then for this side, this is what we would predict. And then you would form another split. You'd say, okay, after you split on gender, maybe split on age, and then maybe split on, I don't know, education level or things like that. And then you would say, okay, for this gender and this age and this education level, this is what we predict. And for this gender, age, and education level, this is what we predict. And you do that. That's one decision tree. And then a random forest, you do the same process, except you're going to say, instead of splitting on gender in the beginning, try splitting on, I don't know, career sector, okay? Those who work in education over here and those who don't work in education over there or something, right? And you random forest basically says the variables that you split on are going to be a little bit random. You're going to get a whole bunch of different looking trees, but then we're just going to average all of them together. Okay, so that's what we have. There's different packages out there. Kind of one of the early packages is Random Forest itself. And then later another package called Ranger came out, which does the same kind of thing, but is much faster. And so if you're going to fit a random forest model, I recommend Ranger over the kind of random forest model. So here I'm going to say make a random forest model. You can set different parameters here, and here I'm going to say make a random forest with 1,000 trees, and our engine is going to be regression. Random forest can be used both for regression or classification, so we're going to say set mode regression. So this is our model. Okay, so we have a linear model, we have a random forest model. When you do a random forest, you don't need to do that much pre-processing. So in a linear model, you have to convert your categorical variables into numeric ones by turning them into dummy variables. With a random forest, you can leave categorical variables as categorical variables. So as far as our workflow goes, we don't need a recipe. All we're going to do is we're just going to specify which variables will be used. So we're going to use the same variables: neighborhood, gross living area, year built, building type, latitude, and longitude. Okay, but we don't have to do any kind of pre-processing variable transformations. So this is going to be our random forest workflow. Okay, here's our workflow. Here's the formula. Here's the model. Okay, and then we're going to fit our random forest workflow to our training data. So let me go ahead and run this. That's the ggplot. Here's my predictions. Okay, and then so I fit the model, and then now I want to measure its performance. Okay, so we will make our predictions. So here I just kind of combine them all just onto one slide, but we take our fitted model, we make predictions using our fitted model, and so this is going to be the Ames Random Forest test results. and then I'm going to create our columns, bind the predictions along with the actual values, okay? So I can see here's our predictions, and here's the our predictions and the actual values, okay? And then we can measure its performance. So here I'm going to something happened. Okay, so I want to measure the root mean squared error, okay? And so using the random forest model, the root mean squared error is 0.0701, and we can compare this to the root mean squared error of the linear regression model, okay? Again, right now, we haven't done any of the cross-validation. We're still just kind of comparing performance on the training versus performance on the test, okay? And so based on these two, we're just going to say, okay, the random forest model has lower RMSE versus the linear regression model, and therefore we would pick the random forest model over the linear regression model. Okay, so that's this is just kind of our first step as far as comparing two models there. Okay, again, we're just doing train versus test, and even though this is kind of a preview of what we've done, we don't actually want to use the test set too often, okay? You really only want to use the test set once, because if you keep kind of using the training and then measure on the test, and you say, okay, well, this model outperformed the other model on the test set, and then you try out another model, okay? And you say, oh, I got even better performance. Okay, let's try out another model. Oh, I even got better performance. You might end up overfitting the test data, okay? So you might end up just fitting, every data set always has some weird quirks. There's always gonna be a couple observations that either have, are outliers or something like that, and that's gonna affect your performance. And if you overfit, you might fit those outliers really well by including some kind of unusual or unnecessary feature in your model, and it's not going to generalize well to new data sets. So to avoid this, we'll use cross-validation, and so we're going to follow the same process, but now we want to compare, make predictions based on the analysis set and measure performance on the assessment set, and we do it for each of our different folds. So we're going to do the same process, but rather than just going from training to test, we will use, our k-fold cross-validation, and we'll ask the system to do this resampling and measuring of the performance there. Okay. So we will take our training data and create 10 folds, and this is going to create our folded training data. All right, and all of the fold information is just going to get stored in this object called Ames folds. All right, and that by having the folded object, this streamlines our process. Okay, there. I just want to kind of take a step back, all right? Tidy models is really great for streamlining the process for the human interacting with this and doing this kind of data exploration. Once you have a model that you like and you want to deploy it in production, you probably don't want to use tidy models, okay? Just because tidy models, well, I mean, you can, but tidy models requires a lot of overhead. Like this Ames fold object takes up a lot of space in memory because of, it kind of stores, all of this 10-fold cross-validation stuff. So, take the model that you've learned and then deploy, kind of a more streamlined version. But anyway, as far as our interaction with it. This is very efficient. So all we do is we call vfold cross-validation. We create this AIMSFolds object, and this allows us to do cross-validation very rapidly. Okay. Now there's a few things you can do regarding how cross-validation is conducted. So you have these control options, and you can control how the resampling and things go. All right. And so in our case, we're going to put in a couple options where we're going to, when it does cross-validation, we're going to ask it to save the predictions, and we're also going to ask it to save the workflow. Okay, and so this is basically, a little bit of overkill. A lot of times you just kind of have it measure your performance on the cross-validation and you're done. But here I want to demonstrate, like, you can actually look at all of the fine details here. Okay, so these are different options, and you can look at the reference on how to kind of control a bunch of the stuff under, control resamples, control the grid search process. There's all kinds of different information there. Okay, so I'm going to just use this line right here to say, hey, store even more information, and this is, for your benefit here of, I guess, kind of showing where all of these numbers are coming from. Okay, so we just take the workflow that you've established. So remember, the workflow is the pre-processing or the variable selection paired with a model. So for the random forest, it's just variable selection paired with the random forest model. We can do it for the linear model workflow. The linear model workflow is that kind of the recipe with all of those steps of, make an other category and all of that paired with the linear model. Okay, so we're going to just take the workflow, and then we call this function fit underscore resamples. It's very similar to fit. Okay, so if we just go back a few slides, we would take the workflow and we just fit it to the training data. So a few slides back, we just said take the workflow and then fit it to the training data. And here, instead of just fit to the training data, we're saying fit to resamples, and the resamples are stored in not the AIMS training data, but the AIMSFolds, okay, which we established on this slide. We just say take the training data, fold it up using vfold cross-validation. That's in the AIMSFold, and then now we're going to do fit on basically the folds. So we're going to say fit resamples and store it on AIMSFolds. Okay, and then we also want to put in just a few options here, which is right here under the control. How should the resamples be done? We want to kind of say save the prediction, save the workflow. That's under the control resamples framework here, and so that's going to be right here. Okay, so this is going to do tenfold cross-validation because AIMSFolds is a tenfold cross-validation object. Okay. And if you use setSeed, it's going to be reproducible. And so because it's doing tenfold cross-validation, you can notice it takes a couple seconds to run, okay, or I guess more than a few seconds, because it's going to do the random forest, which in the beginning, takes a while to process, okay? Anyway, and then you're going to do it for the tenfold, so you're going to do it 10 different times. Okay, so you can see the results of the tenfold cross-validation, okay? So if I do rf underscore results, this is the results of the tenfold cross-validation. And basically, this has, these are 10 different fitted random forest models, okay? So I'm going to go back a few slides. When we fit the random forest model, okay, I took just my workflow, I fit it to the training data, and I have RF_fit. This is the random forest fit to the entire training data set. And basically each row here is basically the exact, like a miniature version of this, okay? It's the same thing as fitting our workflow to the data, except it's going to be fit to, fold 1, or fit to fold 2, fit to fold 3. And, each of these folds is where you're taking a 90% subset of your data, and then it makes the predictions and it calculates the metrics for you. Okay, so it does all of this work of fitting the workflow to the data, and then making the predictions, and then measuring that prediction performance. Okay, it's doing all of that, and each of these is one of those things. And so you can explore any one of these things directly. Okay, so I can say, hey, you know what? Let's look at the metrics column here. All right, so under dot metrics, like I can look at this first one right here. Okay, so I can say take our results, and let's say I just want this first row. Okay, and I can say, all right, let me just let's just look at the third column. Okay, this is going to be the metrics, and I can just extract that out directly. Okay, so I can say, hey, go to the metrics, and then to kind of the result of just selecting this is, it's kind of the structure here feels a little bit strange, okay, because you see all of these things called tibbles, but basically you have this rectangle, but then within some of these cells are like smaller tables themselves, okay? So it's like, when you see tibble here, it's basically a table inside of a table. So here we're saying this first row is the result of one random forest fit, and within this we have we're keeping information about the splits, the ID, the metrics, the notes, and the predictions. And I can say, all right, I want the metrics. The metrics itself is a small table, okay? And so I can say, hey, go to that first row, third column, and it says, yeah, it's just a table. So if you want to extract that table out, you can use the double square bracket notation. We say, hey, let's get that object out, and we can see the table here. And we can see, oh, this is the root mean squared error is 0.0605. If I want to see the predictions itself, I can go to the 1, 2, 3, 4, fifth column. Okay, so I can say RF results. Let's go to the fifth column. All right, and again, this is just going to say, hey, that's a tibble. And so to extract out the tibble itself, all right, the tibble has 234 rows and 4 columns. Okay, so it's, because the way we're doing this split is we say, hey, train on the 2107, make predictions on these 235. Okay, so we can see, okay, what are our predictions? And so we say, okay, here's the prediction, here's the sale price, and it tells you which row we're looking at. Okay, and so we can, if I wanted to, I can say, all right, I want to calculate my residuals by doing dot predictions minus the sale price, and then I want the square residuals by taking the residuals and squaring them, and then I want to how do I extract that? Okay, so here I'm getting my residuals and my squared residuals, and then I can say summarize and take the mean of the squared residuals, and then we want to select MSE, and we want to pull that, and then I want to take the square root. Okay, so here is the square root. Like if I take the squared residuals and then I take the square root, this is my RMSE. Okay, so I calculated the residual, I squared them. I'm going to take the mean of that column. I'm going to select that column. I'm going to pull it out and take the square root. And I get 0.0604. And we can see, oh yeah, that's already done for us, okay? Because if I just looked at the metrics themselves, okay, and I pull out the select the dot estimate, and I just want to pull that column, and then okay, we can see this first number, 0.06048913, right there. Okay, and then I can do it with any of the other rows. If you want to see the other folds, okay, like this fold here, I could have selected the second row, and so you can extract out all of this information yourself directly and get it, right? If you want to see the actual values themselves, you can look at that splits column. The splits, you have the analysis and the assessment set, so then from here you can pull out the analysis, and this you will get the 2,107 rows in the analysis. If you want the assessment set, you can get the 235 rows in the assessment set, okay? So you can get all of the rows themselves directly if you want, okay? Now you don't have to. The whole point of tidy models is that it streamlines all of this for you, okay? But if you want to look at the metrics themselves, all of this directly, you can, okay? So that the result of fitting the random forest 10 times, okay, one to each of these different 10 folds, is all stored in RF results, okay? All of the different RMSE values are stored in this column of tables, okay? The dot metrics column has the RMSE and all of that stuff here. And you can get all of those things individually, or you can call collect metrics and it will take the average, okay? So you can say collect the metrics on 10-fold cross-validation, and it's going to just go ahead and take the average. And you can see, sometimes the RMSE is 0.0605 here. The RMSE is 0.0653. In other ones, it's higher and whatnot. And so when we take the average of all of them, the average across the 10 different folds is 0.0721. And the average R-squared value across all 10 different folds is 0.831. Okay, and so that's under the function collect metrics. Right. Okay, so you get all of that information. So that's great. Okay, so these slides just show like, oh, if you wanted to see the predictions themselves, which I think we went through, like you can call predictions, and if you want to call, you can call this function collect predictions, and you will what this will do. So here, you can get the individual predictions themselves. Okay, so with 10-fold cross-validation, it chopped our entire data set into 10 different sets or 10 different folds. And then the first fold had 235. And so here we can say, hey, take the results, and I just want to see those. And we got row 10, row 27, row 47, et cetera, a total of 235 rows. Okay, and I could have done this, I can do this for, fold number 2 and fold number 3 and whatnot. You can gather all of them together, okay, because eventually all 2,342 rows, each one shows up in one of the 10 different folds. And so you can call collect predictions, and it will gather all of the different folds. So it basically is going to go through all of these different predictions and bind all of the rows. So this was fold 1, okay? And then it will do it for fold 2 and fold 3 and fold 4, okay? And so you can see here we have 4 columns, 235 rows and 4 columns, and you can see the result of collect predictions is 2,342 rows, so that's the entire data set, And then there's a fifth column because one of the columns is which fold it was part of. Was it part of fold 1, fold 2, fold 3, et cetera, et cetera. Okay, and so you can collect predictions there. And then if you want to, you can do all of your different models there. So this is how we go about doing cross-validation here. Okay, we can use this process then to compare different models. Okay, and so we have the random forest model, we have our linear regression model, and here I want to just try out a few different recipes. Okay, so we're going to have basically 3 recipes. The spline recipe is basically the recipe that we've left off with, but we can ask, like, is it necessary? Does it actually make a difference to include these other pre-processing steps? So here I've got 3 different recipes. We're going to pair them with the linear regression model. We'll look at the random forest and things like this. Okay, so for the linear model, my basic recipe is select these variables, make an other category for neighborhoods that don't show up, and then turn those into dummy variables. That's going to be my basic recipe. Okay, and then I'm going to say, well, you know what? I want to include an interaction term. Okay, and to kind of evaluate the effectiveness of this, I'm going to have the basic recipe, and then I'm going to also just take the basic recipe and add one more step. And I want to kind of ask, like, does it really make a difference having this additional step, right? And then I'll do one more thing where I'm going to add the splines. Okay, I can take the interaction recipe and add the spline step. Okay, now, and so we're basically asking, okay, here's the basic recipe where we just kind of select things and make dummy variables. We can add an interaction term, see if that makes a difference. We can then also add, turn the latitude and longitude into splines, see if that makes a difference. Okay. You could also ask, like, can you just do the basic recipe and add the splines without the interaction term? You could also do that. I didn't, but you could, okay, and you'd probably come up with some other name for that, right? Splines, no interaction recipe or something like that, okay? So you can come up with all of these different kind of ideas for pre-processing recipes and say, I want to compare these different recipes, okay? And so here are our different recipes, and we're going to create a workflow set, okay? And so this is going to be a set of different workflows. So workflows are pre-processing paired with a model. And so what we want to do is we want to say, hey, I've got 3 different pre-processing recipes, okay? So as far as this goes, I'm going to create a list. We're going to call this the pre-processing list. And within this, I'm going to take my recipes, I'm going to just give them different labels, okay? So I take my basic recipe, I call it basic. The interaction recipe, interact. Spline recipe, splines, okay? So we're really taking advantage of kind of our structure where everything is an object, okay? And because everything is an object, I can throw those inside lists and things like that. So here is the list of different pre-processing things. And now I'm going to create a workflow set, okay? My workflow set is going to be, I'm going to combine the different preprocessors with the linear regression model. If I wanted to, I could have like 2 models listed here under models, and if I have cross equals true, it will create 6 workflow sets, or I mean 6 workflows in this workflow set. It would do basic with the linear regression, linear model, basic with, I don't know, let's say I had a GLM model, okay? So we would have basic linear and basic GLM, and interaction linear, interaction GLM, and splines splines linear and splines GLM, or something like that, okay? You might wonder, well, like, oh, I thought you had 2 models, a linear model and a random forest model. I do, okay? But the random forest, you don't do pre-processing steps with a random forest. Okay, with a random forest, you just kind of dump your variables directly. It's kind of pointless to do like have interaction terms or spline terms for a random forest. Okay, I guess in interaction terms could make a difference for random forests, but splines and making dummy variables and stuff like that, not necessary for random forest. Okay, so as far as our workflow set, we're going to have a set of 3 different workflows, basically one workflow for each preprocessor paired with linear regression. Okay, and so this we create the workflow set. Okay, and so that's LM models. LM models is a workflow set object. So let me just go ahead and run these code chunks where I create my different recipes, and I'm going to create my different workflow set. And so if you ask, what is LM models? This will say it is a workflow set. And again, Tidy Models puts everything in rectangles, okay, which we like, okay? And so LM models, we have 3 different workflows. And so you could ask, like, hey, what is this? This first row is basically a workflow. Let me see if I can get this out. Let's see. So the so here, the first object is a workflow, okay? And we have the workflow itself. I want that first. How do I get this? Okay, I have to get this thing, and I want the first object there, right? So this, I can extract out the first workflow itself, and we can see, oh yeah, we have a linear regression model paired with the preprocessor and all of this, okay? So, if you want, you can get like all of these different, the workflows themselves. We have this one with the interaction. The one in the third one is has the spline. So we can extract out all of the different workflows themselves. And they're just stored in kind of this table form, okay? Right now, we have the workflows established, but we haven't fit the workflows to the data itself, okay? So right now our results are completely empty. And, okay, and so this is extracting out any of this stuff. So here I can just say, hey, I want the information, LM models, pull out the information, and we can extract out the workflow itself. Okay, and so what we want to do is we want to take this workflow set and basically for each workflow in the workflow set, we want to do the cross-validation, okay? So I'm going to, when we do cross-validation, we call the function fit resamples. And so we want to have Tidy Models perform cross-validation for the first workflow in the workflow set, and then do it for the second workflow in the workflow set, and the third workflow. And so this is handled with this function called workflow map, okay? So workflow map takes a function like fit resamples, okay, or fit, okay, but we want to do it for the cross-validation, so we're going to do fit resamples, okay? And then it runs this function, fit resamples, over the different workflows in your workflow set, okay? So that's called workflow map. So, so what we're going to do is we're going to take that workflow set. There's 3 workflows in there. We're going to call workflow map on it, and then we're going to call tell it to run fit resamples. Okay, there's a few different options here, and so seed is going to help us with reproducibility, and then we'll also ask it to be verbose, and this is going to just produce more output for us. Okay, so we say take the LM models. This is our workflow set. We're going to call workflow map. Okay, and workflow map says what's the function you want to run. We say run the function called fit resamples. Okay, and that performs cross-validation. And when you do cross-validation, you have two arguments, right? When we called cross-validation, we said do it on the aims fold, the vfold cross-validation object that we've set up, and then these are our control options. So just this is slide 34. If I just go back, and when you called fit resamples, basically these were the arguments, and we're using the same arguments here. Okay. So we do that, and it's going to do 10-fold cross-validation on the basic LM, 10-fold cross-validation on the interaction LM, 10-fold cross-validation on the splines LM. Okay, and it just produces all of this output here. And so when it's doing 10-fold cross-validation, it takes a few seconds for each of these things. And it finishes running, okay? And so now, if I ask what LM models is, okay, now we have results, okay? Whereas before we didn't. So the option now, so that object LM models now has the results in the results column. So I'm gonna go back a few slides. Before we ran it, our LM models, our results, it said list 0. These results were empty. There were no results there. Now we have results, okay? Okay, and so we can kind of see like, oh, yeah, what was in there? So I can just say LM models. I can say, what was in option, and we can see what was there. We can say what's in the result. All right, and we have results for each of these things. This looks familiar, right? This is the same kind of resampling results that we did when we did 10-fold cross-validation. So when I did this and I said fit the random forest doing 10-fold cross-validation using fit resamples, the results of that was resampling results, 10-fold cross-validation, and we had all of this, okay? And that's exactly what we see here, okay? Except this is the 10-fold cross-validation for the linear model. Whoops. Okay, so we have, our predictions and our metrics and all of that. This is 10-fold cross-validations for the, this was the basic recipe, the interaction recipe, and now the splines recipe, okay? So these are the results here, okay? And so what I can do is I can, if I want to kind of collect the metrics here, okay, I can combine the random forest results along with this, okay? So anyway, but this is the results of LM models. I can say, let's take a look and let's collect the metrics on this. Okay, and it gives us RMSE values, R-squared values for each of the models. I can say, hey, you know what? Let's just look at, let's filter to where the metric. I only want to see the RMSE values, okay? Oops. Oh, equals. Okay, and so we can see the RMSE values goes from 0.0803 to 0.0799 to 0.0785. Okay, and these are the cross-validation results. So as we do cross-validations, yes, making our linear model more complicated by adding additional steps into our preprocessor does improve our performance, but you know, just a little bit, right? Going from 0.0803 to 0.0785. So we do get performance boosts. You know, not hugely dramatic ones, but they do go down. Okay. And that's what we have. Okay. Again, our random forest, the results of the random forest look just like this. And so one interesting thing is, because everything is kind of stored in the tables, I can just kind of take the random forest results. So remember the random forest results? Okay, these are the random forest results. They're in the same form as this, right? So I can just tack this on, okay? So my LM models looks like this. My random forest results look like this. And so I can convert my random forest results into like one thing of a workflow set. As a workflow set, I have to give it a name. All right, so here's LM models as workflow set. I'm going to call this random forest. Okay, and so this looks a lot like this row looks a lot like this row. Okay, and so we can just kind of bind the rows, and so now I will have a bigger workflow set. Okay, so I'm going to just take the random forest, make it a workflow set, and I'm going to just bind that row to all of the other models. Okay, so we'll just take that as a workflow set, and we get that. And so now I've just expanded my workflow set to have 4 models here. I've got random forest plus the 3 linear models that I have. Okay, and so this is just a table of workflow results. Okay, so we did the random forest earlier, we fit resamples, and we got its 10-fold cross-validation results. Okay, we did a workflow set to create 3 workflows, and we did a workflow map to do 10-fold cross-validation for each of these things. Okay, so the workflow map and the workflow set just streamlined this. I could have done the basic LM, did fit resamples, and I could have done the interact LM, fit resamples, and the splines LM and do fit resamples. But by having a workflow set, all 3 of those things were just done in one command. Okay, so I have all 4 models here, and I can do the same thing. I can collect the metrics. Oops. Collect the metrics. I can filter to metric being RMSE. Okay, and so we have these different results, 0.0721, and so on and so forth. So it does seem like the random forest is the best performing one. And then we have, there's a plot, okay, a function called autoplot, and this will automatically create like a figure that shows the results of the different metrics here. So when you call autoplot on this, something's going on here. Okay, so with autoplot, it takes the RMSE of the random forest, which was 0.0721, and it plots that, and it also gives us the error bars on that, and then we get the RMSE of the different linear regression models. Okay, and we have error bars on there, and you know, whenever you do cross-validation, some of the folds will have less error, some of the folds will have more error, and so that's what these error bars represent. Okay, so we have RMSE, same kind of thing with R-squared values, and so we see indeed the random forest has the lowest RMSE and the highest R-squared values of the different models that we've tested here. So that's autoplot. Okay, is this okay? Does this feel, I don't know, questions about this? I don't know if I'm going too fast or too slow on all of this. Is all right? So again, these are just tools that we have that allow us to kind of streamline this process so that if you have different models, different kind of pre-processing ideas, you can create a set and do cross-validation on all of them with just a few lines, okay? Yes, we can do all of this manually, but manually would be very painful because you have this model, you then have to fit it on this 90% and assess on the remaining 10%. Then you have a different fold and you fit the same model in the 90%, assess on the remaining 10%, and you do it again. And that's just for one model. And then you say, okay, well, here's another model, and then you fit it to 90% of the 10. And so you do fit resamples, and it does the 10-fold cross-validation. You've got a whole bunch of different models you want to try out. You create a workflow set, and then you do workflow map fit resamples, and it streamlines all of that. Okay. So as you have all of these different workflows and the different workflow sets, and you do cross-validation, one of the things that you're going to want to do is to try out different model parameters, try out some different hyperparameters, okay? So you might say, hey, you know what? I want to do a random forest, but I want to see if I'm going to get better performance with maybe 1,000 trees versus 500 trees versus 2,000 trees or something like that. I want to try K nearest neighbors, but I want to try it with 5 neighbors versus 10 neighbors versus 20 neighbors or something like that, okay? I have this preprocessor where I have this recipe, and you know what? When I did this step other and I created an other category for my neighborhood, I chose an arbitrary threshold of 1%. If basically fewer than 1% of the houses belong to this neighborhood, I said that goes into neighborhood other rather than, it getting its own neighborhood. All right, and I said, hey, you know what? When I create the natural spline for the latitude and the longitude, I want 20 degrees of freedom. But maybe I should have used 15 degrees of freedom. Maybe I should have used 30 degrees of freedom, right? So right now, some of these parameters that we've chosen were just arbitrarily chosen. And maybe we want to fine tune our model. And so this next section is about, okay, can we make this tuning process more efficient, right? Because the manual way is you create this recipe and then you say, all right, let's change the degrees of freedom to 15. And then you have a new recipe, and then you're going to go through this process of fitting resamples and all of that. And then you say, all right, well, let's do this again. And you can just imagine in your head, right, like your script having a ton of these different, like, you've copied and pasted the same thing, and all you're doing is you're just changing the number from 20 to 15, or from 15 to 30, or from 1% to 5% or 2% or something. And it's like all of these things are like exactly the same, and it can be kind of frustrating to deal with. So we're going to say, you know what, let's try to streamline this process, okay? And so we use this function called tune, okay? And we're going to put it in and replace those arbitrarily selected numbers. So we're going to go from threshold equal 1% into threshold tune. Okay? And tune here is a placeholder for a number. Basically I'm saying, like, well, maybe it's 1%, but maybe I want 2%, maybe I want 5%, okay? A lot of times you can just use tune parentheses, but sometimes you'll have different things and they have the same name. So later on, like, as we're working with this tunable recipe, one of the knobs will say threshold, okay? And we'll know that threshold talks is referring to this step other, okay? But then another basically knob that we can adjust will be degrees of freedom, but now I've got two knobs, and they're both called degrees of freedom. So here, under inside tune, I'm going to put in an optional argument that's going to name basically the knob, okay? So basically, you can imagine like, I don't know, like a soundboard, right? Like a sound mixing board, right? You have all of these different kind of knobs that you can adjust, okay? Right, so you have, and basically, you want to label each of these things, and that's what tune is doing here, okay? And so we're going to say, hey, this is the degrees of freedom knob for longitude. This is the degrees of freedom knob for latitude, okay? And so all we're doing is we're going to just kind of replace in the recipe some of these arbitrary parameters with tune, and you can do the same kind of thing with a model, okay? So that's what we have there, right? And so when you create your recipe this way, so we're just replacing the numbers 0.01 and 20 with tune parentheses, you can take a look at the resulting recipe here, okay? And so this is called extract your parameter dials, okay? Extract your parameter set dials, okay? And so this will tell you, like, these are the parameters inside the recipe that can be tuned and adjusted. You can adjust it from 1% to some other number, okay? So we have the threshold. Its identifier is just threshold, okay? We have the degrees of freedom, and then this just takes whatever names we gave it, just so that we can distinguish between the longitude degrees of freedom dial and the latitude degrees of freedom. These are just labels here, okay? And so these are going to be like what you can adjust them to, okay? Now, what thresholds do we pick, okay? So here, if you take those parameters, you can extract out what the values are, okay? And it says extract the actual dial, and so that threshold is basically a knob where one end is 0 and the max side is 10%, 0.1, okay? As far as the degrees of freedom, one end of the knob is 1 and then the max is 15, right? So maybe we want to adjust that, okay? So right now our dial's like the lowest setting is 1, the maximum setting is 15 as far as degrees of freedom. So we can see that by using extract parameter dials. Okay, and so if we want to change these things, and we say, hey, you know what? Instead of going from 1 to 15, let's go from 5 to 25. Okay, so we're going to take our parameters and we're going to update. Okay, and we're going to update each of these knobs. Okay, right, like on our mixing board. And we want to just say, hey, you know what? The lower bound of our knob should be 5. The upper bound should be 25. The lower bound should be 1%. The upper bound should be 10%. Okay, and so that's what we're going to do in this next part. Okay, and again, what you pick as your lower bound and your upper bound, these are a bit arbitrary. Okay, but eventually you have to make some arbitrary decisions. Okay, but we allow for some of these things to be, tunable and less arbitrary. Rather than just me saying 1%, let's see if, we can try out a different set of things, okay? So, again, with the model, you can tune parameters in your recipes. You can tune parameters in your models, okay? So, just for funsies, I'm going to just try out another model. Okay, this is a neural network model called MLP. And so let me just show you tidy models. MLP. Do parsnip. Okay, so this is a single layer neural network. The MLP stands for multi-layer perceptron model. Okay, so this is a single feed neural network. If you're in my 102B class, we're basically just working with the simplest neural network, an MLP. Okay, and MLP is implemented in a handful of packages, but anyway, we'll just take say we're going to try out the MLP from the Keras package, okay, for regression, and how many nodes you want, in your hidden units you have. Okay, you can pick an arbitrary number, say I want 30 nodes in my hidden layer, or you can make this a tunable parameter, okay? And so this is, we're going to specify a model here, our neural network model, okay? And we're going to make that a tunable parameter as well, okay? And so in this case, we would have a parameter for hidden units, okay? There's a whole bunch of these different kinds of parameters that can be tuned, and this is under dials, okay? So basically, again, the concept is you have this like mixing board, and you want to kind of try like adjusting these different dials here, okay? And so, as far as different kind of values you can use, they're all kind of listed here. So under reference, you have, you can choose like how many runs you want to do, what's the weight, class weights, degrees of freedom, your learning rate. So in like gradient descent, what is the lambda, what is the alpha, what is, all of these different values you want to use, okay? So those are all different options that can be tuned. So some other examples is, how many nodes in a neural network, how many neighbors to use in k-nearest neighbors, how many predictors to use in a random forest. Okay, so that is showing up in chapter 12 for model tuning, all right? And so this talks about all of these different things as far as like what you want to optimize. And so here, okay, so as you read this, there's kind of a whole bunch of different options here. And okay, and so what we're going to want to do is then we want to figure out like, okay, how are we going to pick the values to use, right? So I want to try out, okay, do I want to try out 5 degrees of freedom for my spline? Do I want to try out 10 degrees of freedom for my spline, 15 degrees of freedom, 20, 25, things like that? And ideally, we can do this in some kind of automated manner, okay? And so there's a few ways to go about it. And you can imagine now we have one model, but just a whole bunch of different parameter values, and we want to try all of these out, okay? And so there's a couple methods. We can do a grid search, and we can also kind of try to do a global search, okay? So you have the space-filling grid, and so this is just an example. Just imagine you have 2 parameters that you want to mess around with. So one is like the threshold for, should I use a 1% cutoff for the other category, a 2% cutoff, a 5% cutoff, or something like that, and you can try out a whole bunch of these different values. And then the other is like, how many degrees of freedom? Do I want to try 10 degrees of freedom, 15 degrees of freedom, 20 degrees of freedom? And so you could say, okay, well, let's try out 1% and 10 degrees of freedom. Let's try out 1% and 15 degrees of freedom, 1% and 20 degrees of freedom, okay? Let's try 2% and 10 degrees of freedom, 2% and 15 degrees of freedom, 2% and 20 degrees of freedom. Let's try 5% and 1, and you have a whole bunch of things to do, and that is the grid search, okay? So the grid search says, try out all of these kind of specified values and create a grid of different kind of value combinations to try out, do cross-validation, and tell me which set of values perform the best, okay? You can also have an iterative search, and this uses maybe a bit of kind of some optimization algorithm that says, hey, let's try 2% threshold and 15 degrees of freedom. Okay, that was this result. So let's just try tweaking one of these things. Let's try 3% and 15 degrees of freedom, and let's see if that got better or worse. Oh, it seemed to get better. Okay, let's try something a little bit higher. Oh, and that got worse. And you kind of do this iterative, just trying out small adjustments. Okay, and maybe that helps you find the thing, maybe not, right? It's kind of again, if you have a whole bunch of knobs and dials to adjust, how do you find like the best set? Okay, sometimes you just adjust one knob at a time, and then you start adjusting, fine-tuning another knob, but then you have to go back and adjust the other knob. Okay, or maybe you can just say, hey, let's try out this and this and this. Let's try out another combination, and oh, that sounded good, or whatever. Okay, and so that's what grid search will do. So here we can use this argument function called grid regular, and you can see with grid regular, it's going to try out basically a whole bunch of different combinations of values. Okay, so here I have 125 different parameter values to try out. Okay, so we're going to try threshold 1%, 5df for longitude, 5df for latitude. Okay, I'm going to try out 3%, 5%, 7%, 10%, and we're going to try it out with 5 longitude df and 5 latitude df, and then I'm going to try out all those 5 different things. And so here basically I'm going to have 5 different values for threshold, 5 different values for longitude, 5 different values for latitude, and so I'm going to have 125 different hyperparameter sets to try out. So this is grid regular. Okay, so I'm going to have 5 times 5 times 5, 125 different things. Okay, so that's grid regular. I take my different parameter grid, okay, the different parameters to adjust, and I said 5 values each. Okay, if I said levels 10, I would have 1,000 things to test out, 10 values on each of them. Okay, but here I just said 5 each. Okay, so here I can do that. If I did 10 levels, okay, I would have 1,000 values, right? Threshold 1%, 2%, 3%, 4%. Okay, 5 degrees of freedom. That might be too many. All right, but that's going to give me a regular grid. And then I want to say, all right, try out a bunch of these things. Okay, another option, rather than saying do a regularly spaced out grid, I can just say, hey, do a random grid, and it's going to just choose random values for longitude, random values for latitude, random values for threshold, and we're going to say, hey, I want 100 different rows. Okay, so that's another option here. And now we get just 100 different random combinations of things. So these are just some ideas here. Okay, and then to try out all of these different parameters, we take our workflow and we basically we use this function called tuning grid. Okay, so tuning grid is very similar to, say, fit resamples, except it's going to try out a whole bunch of these different combinations of factors. Okay, so this is the tuning grid is the function we use for conducting a grid search. It works very similar to fit resamples, except because we are trying out a whole bunch of different values, we have to provide a grid and some parameter information, maybe. Okay, So the grid is going to basically be this thing, all of the different parameter values to try out. Okay, so here is how we would fit it for our recipe here. Okay, so I have the linear regression workflow. So not a workflow set, but just right now for the workflow. Okay, I have the recipe, the tunable recipe. Okay, and I have just the linear model, and then we're going to say take that workflow and then tune the grid doing cross-validation. Okay. And so here I'm doing a random grid with just 50 values here rather than 100. So I'm going to go ahead and I will run this. Set. So we're going to call tune the grid on a 50 size random grid here. And it runs, it's done tenfold cross-validation. And we can see, all right, what's the result of, what's our tuning results here? Right, so it's still running. It takes a while because it's basically fitting 50 different models doing tenfold cross-validation. So it's basically doing 500 sets, fit on this and make predictions 500 times because we've got 50 different values in our grid. We're doing tenfold cross-validation. So it streamlines the process, but it still takes a while. Okay, so we're letting it run. Well, it's going to run for a while. We'll take a look at this is the results of what I got when I ran it earlier. And I think my seed, I threw it off a little bit. Okay, but anyway, we get metrics, right? And we have 100 of these things because each one we fit 50 different values in our grid, right? So I did a random grid where I did like 50 different combinations, okay? And then each of our metrics, we measured the RMSE and the R-squared value, okay? And so we can see these are just the plot of our different things. So there are, I think 50 dots here, one for each of the different kind of random things. All right, it's still kind of running here. All right, so anyway, I've got 50 dots, and so we can see kind of the threshold change for different threshold values. And so it looks like our RMSE performs best as far as having low thresholds. As far as having different latitude and longitude values, it doesn't seem like changing the latitude and longitude DF makes a real big difference, okay? We don't really see a pattern, but it does seem like having threshold values does seem to have a kind of a significant impact on our RMSE and R-squared values. Yeah, this plot got cut off a little bit. But basically lower threshold values of like 1%, 2% for the other category is low, has better RMSE. And if I set my threshold for the other category too high, it looks like my performance goes down, okay? But it doesn't seem like if I have lots of DF for longitude degrees of freedom or a few DF for longitude degrees of freedom, it doesn't look like it's making a huge difference. Maybe if I zoomed in on these values a little bit more closely, there might be a better trend established. But right now it doesn't seem like there's much of a pattern there, okay? After you do this regression tuning results, okay, is this done? Okay, so it finished here. Let me see if I can get this plot. Okay, so you can see different kind of threshold values, and you can see when I have my threshold around 10% for the other category, or really anything higher than it looks like 6%, my performance is quite poor, right? But if it's under 2.5%, so as far as other goes, the other threshold somewhere between 1% and 2.5% seems to be okay. But then once I have that, once I've dialed that in, I don't know if my latitude and longitude really make a difference. So, you know, I could try it again. I could just kind of alter, fit this again. So maybe threshold. So, you know, you'd probably go back and forth a little bit. My threshold levels, instead of 1% to 10%, maybe I'll just try 1% to 2.5%. And then I could run this again. And then we'll, you know, I could say, all right, try out a whole bunch of these different threshold values, different longitude and latitude values. And again, this is going to take forever to run, but we'll let it run. And then, but anyway, after you do that, you can just say, hey, what was a set of parameter values that performed best? And so we got like 0.0137, 25 degrees of freedom, and 6 degrees of freedom for latitude. And then we got 0.0216, 5 degrees of freedom for longitude, and 18 degrees of freedom for latitude. So really, it seems like longitude and latitude DF are all over the place. But these are different threshold values. These were my RMSE values. And so this is just kind of showing the best performing combinations for your grid set there. Okay. All right. We're running out of time. But you got auto plot and show best, and this is kind of summary of the results there. And so you can kind of plug this in and just try different things out. And so I just tried out. Okay. So I said, all right, let's just limit threshold to 1%, and then now I'm going to just try it again with different degrees of freedom here. And then I said, hey, let's just try out 30 things. Does it really make a difference? It doesn't seem like it. It seems like if you have too few degrees of freedom for latitude or something, performance isn't so super great, but maybe our performance is best right around here for latitude DF, wherever this number is. I don't know, around 14 degrees of freedom for latitude does seem to have the best performance. And then you would kind of tune it accordingly, okay? So again, as you try out a whole bunch of models, you're going to find parameters that you want to tune. So we'll have that. Okay, we'll wrap things up here. We'll see you guys on Thursday. I'll talk a little bit more about the project and the data, and yeah, establish your groups. And if you're not in a group, I will assign you arbitrarily to one. Yes, question.
Is there any chance the extension will go from room 2 because this week is midterm week and there's a lot of stuff for this week, so if there is any chance for extension?
If you want an extension, come talk to me. I can grant you an extension. Yeah, no problem.